Anyway, so we'll come back to the class again, ya shabab. So let me quickly try to go over what we discussed before about the application of radial and thrust load. Now, what are we doing here? I want you to understand this very well, is that we have been progressing over the last lectures. First, we talked about the bearing as a simple case, and then we talked about changing the the desired load. Then we talked about the desired reliability. Now here, we're getting more realistic, and what we have is a condition where a bearing, ya shabab, is being subjected to what is a radial load and a thrust load. If you recall, what did I say last time is this. We said that we are going to find an equivalent radial load. Be careful. So that equivalent load is only radial. The magnitude of that equivalent radial load is like now the desired load in the bearing, and we can use it in the equation, which can give us C10. Because if you use the equation to find C10, the catalog value, it is structured and built for radial load. And now what happens if we have a thrust load? There is no C10 axial C10 thrust. There isn't. There is only C10, which is coming from radial. And what did we say? We said that basically we invented a relation, okay, or a relation was invented by somebody, which says that if you look at the ratio Fe, this equivalent, by the way, the equivalent load, how do we determine it? It's very simple. Assume that you have a bearing and you applied a radial load and axial load, both of them. And then you run it at a given specific speed. And then you achieved 2,000 hours of life. The question to you is this: what should the only radial load, which we will call it Fe, because it's different than this, what is it that will give you 2,000 hours? That's it, more or less. Okay, so we said that the ratio Fe divided by V multiplied by Fr, V is the rotational factor, which is 1 if the inner trace of the bearing rotate, 1.2 of the outer one rotate, and it is always equals to 1 if we have a self-aligning bearing. Now let's put V aside, and then we think about Fe as in comparison with Fr. So that question was this: if we apply a thrust load and put the ratio Fa divided by V multiplied by Fr. In the same sense, if I ignore V and I say that it's equals to 1, and if I apply a little tiny Fa compared to Fr, then the value of Fe, okay, that will generate this 2,000, although you applied live, is not very much different than Fr. In another word, up to a ratio of Fa divided by Vr equals to E, Fe is almost the same as Fr. So the equivalent load, so you will always say, oh, that thrust load is too little. So use FE as the load and go and get the catalog. FE is the same as FR. There is no difference. That little tiny thrust is not going to make any difference. You will end up having the same life, although FE equals to FR. That's the idea. And this is represented by the line which is equals to 1 for this ratio, which is the same as this. But when you reach a certain limit, that is no longer valid. If A become bigger and bigger and bigger, in that sense, you have to increase FE in order to obtain the same life, because the damage now is coming from radial force and thrust force. That's the story. So we came up with this relation.
Doctor,
yes?
the V is constant.
The VE?
The velocity.
Sorry, the E?
The V.
The V here is not a velocity. V is the rotational factor. It is equal to, this is the rotation factor, and it is equal to 1 when the inner ring rotates and 1.2 when the outer one rotates. Remember here, we're not arguing about the rotation. The rotation speed is going to be the same for if I compare these two bearings to make a realistic comparison, apple to apple. I am not changing the speed here. I want the same life, but I want to know what is the same life if I only apply FE with respect to an application of two other forces, which is one of them thrust, one of them is radial. You understand? So
Doctor,
yes.
Up till point E, FA is insignificant, but after point E, it becomes significant, so we have to increase FE. Is that?
That's right. That's right. That's right. By the way, you will find that FA may not be too, I wouldn't say it is insignificant. That's it. Yeah, that's it. That's the better explanation for it. So there is a limit after which FA become damaging in a way. You cannot just call FE equals to FR. That's it. That's the story. So the equation, I want you to recall this, is written as this. We are going to use this equation in an example, and you are probably going to ask a question. Like, if you look here, this is FE, so this is the equivalent load. Ultimately, ya shabab, we are coming back to the same story. We want to know what is the applied load, and when we know it, we are going to substitute it as a desired load, and then we will know the catalog value. That's it. That's it. Now, yes.
Can we assume FE as a von Mises when we have shear and axial load?
No. No. FE here is coming from this experimental factors. If you look, that relation is coming from experiment. It is not a state of stress where we have multiple loads and those loads generate tension, shear, compression, and so on. And then we assume that there is an infinitesimal point, and in that infinitesimal point, the state of stress is this, and then we use von Mises to take an equivalent load. No, this isn't the case. Actually, here, we're talking about forces, which is not the same as stress. So be careful. When you apply force, the force is constant everywhere, but the stress changes depending on the geometry. So be careful about that. Okay? Now, so what happens over here? Of course, ya shabab, just to answer your question over here, things are being built here in terms of forces, and we're not jumping to stresses. And because obtaining stresses is not straight, is difficult. you sometimes cannot even find the stress because the geometry is so complex and you need to run finite element. And in the industry, people want fast answers. They know F and that's it. They know RBM, they know life, they know what is it? Percentile and so on. So this is handy calculation, something that will go right away in the practice. So let's not delay this further. So this equation has an index I, which is equal to 1 when we are, this is E, when we are in the side, left side, this is I equals to 1. When we are on this side, I is equal to 2. So it's a combined, this is combining these two equations in one. Okay? Now, so what is xi? What is yi? This is something we are gonna see. If you look over there, we have here a factor which is called C0. C0 is the same as, or let me say, it's similar to C10. The difference is that this is a static factor while this one is a dynamic factor. That's all. So if you look over here, just quickly, you will see that the ratio of FA over C0. So C0 need to be known. It's given by the manufacturer because they apply the static load on the bearing, and at a certain point they say, okay, stop, that's C0. This is when the damage starts to appear. So that is tabulated value. Then we have E. So E can be determined by knowing FA over C0. And then we know, okay, either we have a case on the left-hand side, and in that case, we substitute I with 1. So we have x1 and we have y1, right? But y1 for that case is equal to 0 for one single reason, because it's a straight line, there is no slope. Why is the slope? We are on the left-hand side of E. But if you are on the right-hand side, then you should have an x value and a y value. But apparently, since the line goes like this, x value is going to be the intercept, so the intercept is the same. Well, x2 is the same, and y2 is changing depending on the loading. Okay, so so what happened? This is just some recommended life. So for example, if you say I want to put a bearing for a machine which ran for this much, 24 hours and so on, then you should be expected to you know, have a life which is between 100 to 200 kilo hours. And that's how you go and you size the bearing based on this life. Because the question is, how much life do you want? You can't just say 10,000 years. It doesn't exist. So you need to be reasonable, and you need to know how much is that reasonable number. Okay, so this is some recommendation. Here in the second table, we have a list of AFs, the application factors, starting from 1 all the way to 3, depending on the machine and the application. So I'm not going to spend time on here. Let's go right away to the example. So this example says we have an SKF, which is now you know that this is a popular brand for bearings. Now look, in this problem, the bearing was picked for us. And when the bearing is picked, it means we know that this is a bearing number 6210, and it is angular contact ball bearing. And what happens here is that we know that FA is equal to 400 pounds. Remember this number. Why? Because FA is the thrust load, And the radial load, FR, is equal to 500 pounds. The question is this. If you have a radial force and a thrust force, what should be the equivalent? That's the question, right? So the equivalent is not just the summation of both. It's not like 500 plus 400 is 900, okay? And it is not also the square root of 400 square plus 500 squares. If it is this way, then why did we discuss the equation FE equals to XI VR plus YI multiplied by FA? Why? So the mix between the FA and the FR is not either addition or a square root, which is a resultant vector. It is not. Now, what does it says here is that C0 is equal to how much? 4,450 pounds. Not strange, because the catalog number now, you picked the bearing, you know what are the catalog values. C10, the rated dynamic load, is 7,900 pound force, all of this pound force. And what do we want? We know that ND, the desired speed, is 720 revolution per minute. What do we want? We want L10. How much? Italic L means it is in hours. 10 means, italic L means it's in hour, and 10 means it is a 10th percentile, which means a 90% reliability. Now, if it is 90% reliability, this means I don't need to use Weibull distribution and so on and so on. All what I need to do is to say, okay, I am going to go back to the first equation, which says C10 is equal to what? FD, the desired load, multiplied by L desire, N desire, and then 60, divided by L rating, N rating, and 60 to the power 1 over A. Now, A is equals to 3. Why? It's a ball bearing. It's not cylindrical. It's not tapered bearing. Okay? So this one is known. And now this whole thing is 10 to the power 6. A million revolution. احنا قلنا يا شباب, we said before that Timken bearing has a different rating for life, but other bearings in general have a 1 million revolution. Now in here, if you look at this, we know how much is this. This is 720 revolution per minute. This is a conversion factor we don't care about. This is the question. This is the question. That's what we want to answer. So this one, we said it is a 3 for ball bearing. What is C10? Is here. So in order to solve for LD, the desired life in what? In hours, which is, by the way, the desired life here is going to be L10. Why? Because everything here is based on 10th percentile. So desired life is the same as LT. But it doesn't matter as far as you know that the unknown here is LD. So what remains is FD. FD is the desired load. The desired load, you can name it in your head as the actual load which is being applied on the machine. Is that right? Now, the machine is subjected, be careful, FD is supposed to be a radial load. But we don't have a radial load. We have 400 and we have 500. So which one of them you should use? Neither. you need to go and combine them now. And this is what the question is all about. So in order to combine them, we go back to the table. I want you to see. Now, V is equals to 1. Why? In the question, look, it was a little bit twisted. It says the outer ring is stationary, which means the inner ring is rotating, which means V equals to 1. Is that right? So V is equal to 1. What is F? A divided by C0. If A, we know it, it is 400. C0, we know it, it is 4,450. So how much is this ratio? 0.09. We go back to the table and we look. We have 0.084, not 9, and we have 0.11. So what do? We want to find what is the corresponding value of E, because remember, E will tell me, should I use index I equals to 1 or should I use index I equals to 2? So I will go put the 0.084 and then the 0.11 and take the ratio I obtained and put it in the middle. You know what I'm doing, right? Interpolation. I'm not going to teach you this. So here, what is the corresponding value for this? E is 0.28. What is the other one? Is 0.3. And then here you go. From the interpolation, I got my E. Now E is equal to how much? 0.285. So I'm going there. I'm going to mark this 0.285. Good. Now, the x-axis is equal to FA divided by V multiplied by FR. I know FA, I know FR, and I know V. So let me calculate it. And what did I get? Oh, I get 0.8. I get 0.8. Now, everybody knows where 0.8 here. Somewhere. Is that right? What does it mean? I am to the right. So, just to remind you, this is the marker for number 1. If E over V multiplied by FR equals to 1. And this is supposed to go the same value until I reach over here. The E. This is E. And then the curve will go like that. So I am being governed by a relation with an X and Y. Then, ya shabab, what will happen? Now I know that I am in here. I am not on the other side. Okay? So let's extend the lines of the table. So I'm going to go there and see, oops, I have this. I mean, X is equals to 0.56, which is the same for all. So I don't worry about it. Okay? Now, so over here, I got this 1.55. And then going the same over there, I get how much? 1.45. Why I'm doing this? I want to know what is y2. So I write the same factor FA over C0. Here I put 0.155 and here I put 0.145. 1.45, 1.55. In the middle, that's y2. Good. So by interpolation, I found that y2 is equal to 1.527. Good. Now, if you go back to this equation, oh, I don't have it. Just if you go back to this equation, you will see that you know FA, you know y2, you just determine it by interpolation, you know FR, you know V, and X is 0.56. So what is the unknown? Fe. So you go back now and you do exactly that. When you substitute this, look what you got. You got 890. It is not the square root of 400 plus square plus the 500 square. It is not 400 plus 500, which I am talking about these guys, huh? This one and this one. It is skewed. It's more toward the sum, but it is less by a little bit. Is that right? Now, this FE is what you desire now. You go and call the bearing company, and you don't need to tell them that I have FA and I have FR. You just tell them I have a bearing with a load, a radial load, equals to 890 pound force. You see that? So let me zoom in here. This is very important, ya shabab, for you. So, okay, right there. Now, we just did that. I made the argument earlier that we're going to use this equation. The only thing is we are going to replace FD by FE. That's the desired radial load, which inside it has the recipe, the combinations of FR and FA. The rest, as I told you, the rated is 1 million. So this is 60, this is ND, this is C10, which is given by the catalog, and FE is what we determined a minute ago. And in the end, what did we get? We got the life in hours, which is 6. Oh, the screen sharing got disconnected, ya shabab. Sorry about this. Something is going on with it's coming up. Okay, so what did we get? We get a life of 16,150 hours. Understood, ya shabab?
We replace
Yes.
FT with FE because all the catalog data is based on only, or tested in only a radial load.
Yes. So this is a way to combine both effect into one single force, which is FE, and then go and use the catalog. So until now, it is a winning situation. Why? The companies are producing their catalog based on relatively simple testing, which is radial load, speed, and reliability, and so on. But of course, they spend time to tell us what is X, what is Y, and so on. But for us now, it's very simple. We just combined the effect, and we were able to go along with it. Now, I just, yes, anyone?
Third question.
Yes. When shouldn't we use the 10 to power 6?
What?
I mean, we substitute in the denominator in the first equation with 10 to the power 6. When shouldn't we substitute it?
This is the rated. This one is L capital 10, which is equal, which is in revolutions. And we said that for most bearings, except Timken, it is 1 million cycles, 1 million revolution. So that's it. Down, okay? We use the factor 60 L, we use 60 L10, and then N desire. because we wanted to find the life in hours. That's it. But we can also convert it to revolutions. It's fine.
Okay, thank
Doctor?
you.
So L10 is the same as LD? Italic
Yes.
L?
Yes. Why? Because the desired life that we are calculating is based on what? A 10 percentile. That's it. Yeah, I don't want you to be confused when you go and look at the equation and you think that this is unknown and this is unknown. No, this is the unknown, LD, the desired life, and the LR is the rated life by the catalog. Okay, Shabab.
Doctor, is table 11.3 not important to our course?
What is it?
Table 11.3, cylindrical roller bearings.
Table 11.3. Did I put it here?
No, you didn't. There are two
No.
pages. Yeah.
Oh, this is important. It is the catalog, an example for the catalog for the bearings, and it is you would never use the slide to go and find a catalog. Whenever necessary, I will bring it up. Do you understand? But that's a copy of a catalog. That's the only catalog like table for bearings available. We have another one for tapered. Let me see it now. So it's not that it is not important. You have to be very careful. But here, yeah, it is the cylindrical roller bearing. Yeah, that's another catalog for the cylinder. We have a catalog for a ball bearing. This is an angular ball bearing, which is 11.2. So whenever we need them, we'll come back to them. But you have to be very careful. It's not like the slides are, including. I can't include indices, and I will try my best to do so to make a slide, convenient. But some of the tables, like for the tapered bearing as well, it's like 2 pages or so. So it's very hard to squeeze them in a slide. You better refer to them in the book. Okay, let's move on.
What,
I have to move
what
on.
other cases if the ring, if the outer ring is not stationary?
What is what?
Other cases, can he give us inner ring stationary?
No,
or...
listen. Depending on your application, you may have the outer ring rotate. You may have the inner ring rotate. That's totally dependent on the application. And I will try maybe next class to bring you an example for this. I don't have an example out of my head right now, but you have the bearings. Either you fix the outer ring, like similar to most shaft, the outer ring is fixed to the casing, and the inner ring is attached to the shaft, and when the shaft rotates, the inner ring rotates. This is the most common case. The other case is if you imagine that the shaft is fixed to the bearing and the shaft is fixed, but the whole thing rotates around it. I need to bring you an example. I don't have something in my head. Okay. All right. Now, let's move on, ya Shabab. If you have a further question, you can note them down and ask me later. What are we going to do now? We are going to, in this section 11.8, we are going to have an example about, a complete example about how do we select ball and cylindrical roller bearings. Okay. So this section has a 1 paragraph and then a complete example, because what you have here is a realistic situation. And by the way, most, like 80% of this question, the solution is on finding reactions, which is now for you like 001. So however, just to get you engaged, I am gonna spend the rest of the class and little bit more in the next class talking about how do we do them. But what we have here is this roller. This is actually like a squeezer. What's a squeezer mean? It means that if you put something in the back over here and you push it under this roller, it will come out here from the other side, of course with different thickness. So you squeeze things. You can think of it like a rubber, metal, whatever it is. So we know that when this roller squeeze things and they come out, this would result into two actions. The first one, there is, because of this rotation, and when the material gets in, there is going to be a force pushing this material to the other side. Okay? If you remember from manufacturing, this is due to continuity equation. So what happened? You will have a P, a force, which I just circled on this graph, pushing toward that direction. And when the material gets squeezed, the material will react against the roller and it will push upward. And that's why we have a concentrated force acting on the upward direction. However, this example, I got it from the book, and it was very hard to scan with the scanner. What we were given, the distribution of the load along this line. So a distributed load like this, and a distributed load like this, which makes sense, right? That's a distributed load. When you push forward, there is a distributed load pushing the material as it is being squeezed, and while it is being squeezed, there is a distributed load. I should point to the distributed load in the butt there, here, with upward, just to be in line with the convention of the book. So this is pushing upward. Now, as you know, the distributed load is given as, let me write it with a 5.25 Newton per millimeter. And the other one, if I'm not mistaken, is 4.25 Newton per millimeter. So once we multiply by the length, we get the force. So just to walk you through, what we need to do here is this. We've been given the distributed load. We've been given the speed of this rolling, which is 300 revolutions per minute. We want a desired life of 30,000 hours. 30,000 hours. We want to use an application factor AF of 1.2. We need to use a pair of angular contact bearing ball bearings. The bearings will sit one here and another here. Now, as you remember from machine design, we consider that bearings will allow a little bit of rotation, and for that reason, they will produce only reaction along x-axis, y-axis. In this direction here, we have a reaction along the y and the z. There is no thrust, lucky for us, no thrust along the x-axis. Ultimately, the bearing, ya shabab, is circular. And when you, as a human, assume that this is y and this is z, bearing doesn't care. What bearings care about is the resultant of this. Apply FR along this line, that line, it doesn't matter. The bearing will feel the damage because of that radial force. Okay, so the whole problem here is about finding the reactions in order to get the resultant radial load, and then use the radial load to find bearings for A and B. You see that? And it says that we want a reliability, a combined reliability of 0.92. Good. Now, in order to do this, what we are gonna start, let me just pull up my notes here so I can write comfortably. What are we gonna do is this. We're gonna start by finding these forces. Of course, when you multiply a distributed load by the length is 200 for the roller, ya shabab. Then you will get a concentrated load acting on the middle. So PZ in the Z direction is equal to the distributed load, which is 4.2 Newton millimeter multiplied by 200 millimeter, which is the length of the roller. And this is going to give you 840 Newton. Good. Then we have a PY, which is equal to how much? The other distributed load is 5.25 Newton per millimeter multiplied by 200 millimeter, which is equal to 1050 Newton. That's good. Now, if you look back to the drawing, you will see that the diameter of this roller is given to us, right? And if you look at it from the side, this diameter of 100 millimeter, when you have the force PZ acting on it, and you multiply by the radius, you will get a torque. Now that torque is not alone. Everything here is in equilibrium, ya shabab. So that torque will be opposed by the torque resulting from the gear. Why? The gear has the same story. It has a force like this, which will generate F tangential and F radial. And when we multiply the radial force, the tangential force, by the radius of the gear, we will get an opposite torque. And that's how they both cancel out. We have a balance. The torque diagram will go like this, and then it will end up 0. So remember that the Z force over here, so the torque is equal to PZ, which is 840 Newton, multiplied by the radius of the roller, which is 50 millimeter, and this is going to get you 42,000 Newton millimeter. Now, since we know that torque along the X direction, the summation of the torque along the X direction is going to be equals to 0, okay? Then we say that minus 42,000. Why minus? Because this torque, if you point with your hand, it will point toward the negative X. And then the other one, now recall, the gear is like this. If you remember from 307 when we did the project, if you took it last term, we said that this is the pressure angle 20. So you will have a radial force like this and the tangential force. The tangential force is the cosine. So what are we going to have? We'll have 38. Why 38? 38 because the gear has a diameter of 76. You divide that by 2, you get 38. So you have 38 multiplied by the force multiplied by cosine 20, which is equals to 0. What do you get out of this? You will get the force. The force is going to be equal to 1,176.2 Newton. We're not done yet. After finding these forces, we need now to go and run multiple calculations for the moment in order to find the reactions. So, for example, what are we going to do? We will go and say, what is the sum of the moment about point O, that's point O, along the Z direction? So if you look, this is the Z axis. So we want a rotation around it. What are the forces that cause a rotation around it? This force. This force, right? What else? The radial force goes in the other way. Then what do? We find the sum of the moment about O with respect to Y. Now we want rotation along this direction. What are the forces that causes rotation along the direction? This force, and the tangential force as well. And when we do this, inshallah, next class, we will be able ultimately to find the unknowns. What are the unknown? R, O, the reaction here along the Y, along the Z. The reaction at A along the Y, along the Z. Then we take their square root, we get the resultant. Then we use these resultants to go and find proper bearings. You understand? So until now, we didn't talk about bearings at all. We're just finding reactions and forces. That's it. Okay? I think I'm going to stop here because I have like nearly 2 minutes. So let me stop the screen, and then I am going to share my, what is it?